inviting me to give those lectures. It's a bit unusual for me because I am what are called high energy physicist, and though I was sort of trained somewhere in between high energy physics and statistical mechanics, and when I was a graduate student there wasn't that much of a distinction. When I was asked to talk about statistical field theory, so I tried to think of what this could be. I mean, there are several books which have a title, Statistical Field Theory, a very famous book by Parisi about this. So I looked at that book. I mean, it's just fantastic, but I didn't quite think that it's that appropriate. So what I thought I'll do, I interpreted this thing as saying that I'll tell you something about quantum field theory, which could be of interest to people who are working in statistical mechanics and areas of condensed matter physics which deal with statistical mechanics. I said I'm a high energy physicist, and high energy physicists have a reputation. Some people consider it as a good reputation, some people consider it as a bad reputation. And the reputation is, or at least the description of a typical high energy theorist, is that they deal with what they call fundamental constituents of matter. Now, this is a very loaded term which has a lot of controversies of what is fundamental and what is not. But in all fairness, they deal with things like electrons and positrons and quarks and leptons and W bosons and Z bosons and so on and so forth. And there is a prevalent idea among mostly people outside the field that the aim is to figure out the laws of these fundamental constituents, and from those laws we want to derive the laws which govern the normal behavior at our energy scales. Well, in some basic sense, that indeed was the aim of corpuscular theories. Like, I mean, Einstein began his career by asking the question, how do I know atoms are real? That's why he invented the field of non-equilibrium statistical mechanics with his paper on Brownian motion. So in a sense, that is indeed correct. Indeed, in principle, of course, if you have the laws of quarks and leptons, you know what are the laws which govern pions and whatever hadrons you think about. What is less appreciated is that high energy physicists actually spend a lot more time and effort in trying to figure out what can we do without knowing the details of the laws at very short distances. What is it that makes it possible, in fact, to do physics at all? I mean, if it were true that to solve the problem of a hydrogen atom, you needed to know quantum chromodynamics or quantum gravity or string theory or whatever, I think, of course, the whole thing will be hopeless. So the whole idea is that what is it that tells me that I can still do physics at scales which are of relevance to us, knowing that there are fundamental implications of the scales, and yet make accurate predictions about nature. You probably know that one of the most accurately known numbers in nature is G-2 of the electron, which is known up to some ridiculous number of decimal spaces by experiments and exactly verified by calculations in quantum electrodynamics. And we know quantum electrodynamics is not the theory at arbitrarily short-length scales. So why is it we are able to do it and produce such accurate numbers? So let me actually begin by talking about the hydrogen atom. Now, the hydrogen atom, we all know how to solve the hydrogen atom in many possible ways. So there is a proton and there is an electron which is going around, and if you just look at the problem in natural units, I'll always use units h bar equal to c equal to 1. In natural units, basically there are two parameters, two numbers in the problem. One number is the mass of the electron. And the other number is called the fine structure constant, In these units, it's just the square of the electron charge. In these units, the square of the electron charge happens to be 1 upon 137. Generally, it's E square by h bar divided by h bar c. And it turns out that if you want to calculate properties of a hydrogen atom, not to arbitrary accuracy, but if you ask a question, for example, what is the Bohr radius in a hydrogen atom? Anybody knows what's the Bohr radius of a hydrogen atom? Very good. How does it depend on the mass of the electron? See, that's the whole point. The whole idea is you don't have to remember anything. The whole idea is you try to figure out something. And so let me give you a quick way of figuring that out up to some numbers. In these units, if these are the only things, and I'll try to we'll try to understand why is it in the hydrogen atom only these are the only things of relevance. Why is not Newton's constant of gravitation or the mass of the W boson or what have you at high energy scales are relevant to this problem? We'll understand that. That's the main purpose, in a way, the main purpose of understanding quantum field theory. But if you try to figure out what is the radius in these units, mass has units of inverse scale, so its mass has the same units as energy is the units of length inverse. So you would imagine it goes as 1 upon the mass of the electron. And if you just solve the problem of hydrogen, it indeed goes as mass of the, indeed inverse as the mass of the electron. But it has another thing in it, which is a little bit uncomfortable, which is it must depend on alpha somehow. That, of course, you cannot figure out by dimensional by dimensional analysis, right? Because that's a dimensionless number. How can you put a dimensionless number using dimensional analysis? It turns out the number is 1 upon alpha, and roughly speaking, the reason is that if you, you sort of know it should depend on inverse of the electron charge, because if the charge was very large, then the atom would have shrunk and the radius would have been much smaller. But the fact that it is 1 upon alpha but not 1 upon alpha to the power 4, that's a question you have to figure out by dynamics. And that this doesn't actually tell you that. Okay. Similarly, if you ask, what is the typical energy scale of the problem? What are the energies levels of a hydrogen atom? If these are the only things which are present in the problem, you would imagine they are proportional to, again, mass of the electron, because in these units, this is the only scale which is there. And there is also some function of alpha here, which again we cannot calculate. It turns out to be square of alpha. With a little more thinking, you can figure out these powers of alpha. But the important point is that to understand why is it that all the other, in particle physicists have a book which is called the particle data book, which is brought out by Reviews on Modern Physics. It's actually pretty thick. And it has hosts and hosts of particles with all kinds of numbers in it. None of them is relevant to this problem. Intuitively, you sort of understand why things wouldn't be relevant to this problem. And as I think Kiran mentioned in his talk, the example of hydrodynamics, where basically all liquids, like even all the way from water to alcohol to even mercury, sort of basically satisfies the Navier-Stokes equations. And there are some parameters in the Navier-Stokes equations which are quite different, but there are few of them, 2 or 3 of them. There is several viscosities, a bulk viscosity, a shear viscosity, some density. That's basically about it up to second order of nonlinearity in the Navier-Stokes. It is indeed true that pretty much like the atomic theory, Boltzmann succeeded in using, what is going on? My throat catches it. How about this? Good? So it is indeed true that if you knew the details of the liquid, the molecules they are made of, the way they scatter, you write down Boltzmann equation or what have you, you will be able to calculate these numbers Those numbers are indeed produced by microscopic physics. That's the whole idea it goes. But why is it that there are so few numbers? I mean, why is it that first the laws are universal? They look very different from Schrodinger equation, though. I mean, it's you might say it should be derivable for Schrodinger equation. Nobody in their right mind would even try to do that. So why is it there are few of these, and the other scales do not appear in physics, in the physics of the problem? From this point of view, quantum field theory is a theoretical framework to understand why this is so, to understand why is it, in fact, it is possible to do physics scale by scale. So why is it that in order to do physics at the scale of an angstrom, I do not need to know the details of the physics at the scale of a Fermi? Or if you want to know the scale of the physics of nuclei, you really do not know the details of the physics at the level of the weak interactions and so on. Okay. This kind of, we call it decoupling of scales, the fact that only a small amount of physics at the high scale survives at low scales. This kind of thing is, of course, even a mathematical property of many differential equations, so it's not just a feature of quantum in quantum mechanics. But in quantum mechanics, this actually plays a very important role, and it lies to the key for predictability of quantum field theories to describe nature. So what I'll try to do in this course is to introduce the concepts and some of the technology which is used to understand this whole theoretical framework was slowly arrived at in the mid-70s, and it's called the renormalization group. So it's developed by many people, and it came as a incredible confluence of ideas from statistical mechanics and from particle physics. It's one of those very fruitful merger of ideas which gave rise to this, what I would like to call, in fact, a paradigm shift in the way we think about physics. Modern quantum field theory is basically this. So what I'll try to do is to lay out the foundations of this kind of thinking and some of the calculational tools which you need to understand what's going on here. Okay. So that's the aim of the course. I don't know how much I'll do that. So what I'll do today is to set up the problem, give a brief overview, and tell what I aim to accomplish at the end of 6 lectures. So first, I'll make it very quantitative in terms of functional integrals, the connection between statistical mechanics and quantum field theory. I'll deal with classical statistical mechanics, in fact, though the extension of the idea to quantum statistical mechanics is not very different. So I'll set up the methods of doing that. So to begin with, let me just tell you what the framework of these two areas are like. A typical lecture in statistical mechanics starts with pictures which look like this. There is a lattice, there are spins, sometimes there are things living on the links, and then you write down a Hamiltonian. And so suppose there are spins, okay, spin up, Ising model we just talked about, so let this be an Ising model. So there are some spins I'll call Si, and you start with this Hamiltonian, and in classical statistical mechanics you compute an object which is the sum over all states times beta times this Hamiltonian. Beta is the inverse temperature. You compute from that a free energy and various other things from it. Now, if this looks very different from the kind of things which you write down in a typical particle physics book of quantum field theory, you write things like phi of x and t, where this is a function of space and time. We call them fields. And you go on to things like, these are called gauge fields, vector potentials. You write things like, I don't know, metrics and so on. They look pretty different, and clearly these are functions of continuous variables which are time and continuous variables which are space, and there is a whole mathematics which you describe, which you discuss in order to discuss this problem. Why would these two things have any relationship at all? Particularly, I'll emphasize the fact that there is no lattice here. I mean, there is no lattice here, and there is no, we are talking about, typically most of the talking about ill-defined objects like two of these fields sitting on top of each other. In quantum mechanics, it's a very bad object, whereas this is, completely mathematically well defined. I mean, there's no, you can write a computer program and program this thing in to calculate. That's what people do. This is very hard to do that. So why is it this problem has any relevance to that problem? If you think about this problem, and suppose the thing was in some ground state, and let it be a ferromagnet, so all the things are aligned. And you take one of the spins by hand and tickle it a little bit. Of course, the moment you take one spin, it tickles the next one, and it tickles the next one, and the disturbance sort of goes to some distance. And there is a quantity which we usually define in statistical mechanics called the correlation length, which sort of quantifies how big is the effect of a change at a particular point. For example, if I write SI, it's called the 2-point function. So that goes as, typically, if you measure, it goes as like the distance between them by some quantity, which is, I'll call the correlation length. If you take a system like this and put it in some generic temperature and ask me, what is the typical correlation length of this system? You'll find, okay, it's 10 times the lattice spacing, or 20 times the lattice spacing, maybe 50 times the lattice spacing, sometimes 2 times the lattice spacing, but it's of the order of the lattice spacing. So generically, you have a correlation length which is of the order of the lattice spacing. Now, I said the field theory doesn't have any lattice in it. I mean, it doesn't look like it has any lattice in it. It looks like you're going to do something with some quantum mechanics with functions, continuous functions like this. But that's actually a lie. And the reason why it's a lie was actually first realized by Dirac many, many years ago. Dirac was the person who laid down the foundations of quantum field theory. And very early on, Dirac realized that it's a very ill-defined procedure to take two functions and multiply them together. Like I take two of these phis and I write a function which is phi square and phi fourth. In classical field theory, this makes perfect sense. It's just a square of some functions. But the moment you think of these phis as operators, as you usually need to do in quantum mechanics, this doesn't make much sense, because you're talking of taking an operator, roughly speaking, is something which has some mean value and a lot of fluctuations around the mean value, and then you place on top of another operator exactly at the same point. It's a very, very bad thing to do. Okay. In the old days, so this problem was recognized, and when people first started doing calculations with quantum fields. The first calculations were actually done in quantum electrodynamics by Dirac and Heisenberg and Bethe and all those people, and they of course found answers which are complete nonsense. And those answers were complete nonsense because if you calculate physical quantities, like you calculate like okay, what is the correction to the mass of the electron? Answer, infinite. If you calculate how does a photon, Compton effect, how does a photon interact with an electron? If you calculate in this theory, the answer is infinite. Okay. So this used to be called the problem of infinities, and people invented a mathematically self-consistent, not necessarily meaningful, but a self-consistent way of subtracting out these infinities. This has a name which was called renormalization. What this procedure, this, and I will not describe the sort of the old way of doing it. What it really means is that you take an infinite quantity and you subtract it, another infinite quantity from it, and you get a finite answer. Doesn't sound very good, does it? No, it doesn't. Okay. But it makes perfect sense. That's one of the aims to understand why that procedure is completely correct. Okay. Very soon on, of course, if you have an integral, for example, if you do an integral like I don't know, dx by x, say from 0 to infinity, this integral is divergent both at the upper end, it's a log x, so log infinity is divergent, log 0 is divergent. And so the good way of thinking of this integral is to take this to be infinity and this is to be lambda, and then you have some finite quantity. The analog of this quantity x in quantum field theory happened to be momenta of particles. So you have a process, for example, a classic process was like a scattering of two particles. So you have one particle moving with some momenta p1, there was another particle with the momenta p2, and it turns out that I don't expect you to know this. There's something called a Feynman diagram which gives rise to two other particles. This is scattering of two particles into two other, scattering of two particles from each other, and this round thing in the middle is that it's just an indication that what this thing actually involves is an integral over some momenta, some d-dimensional momenta times some function of momenta, and if you did this integral always diverges. The integral diverges because you should allow for all possible momenta in the problem, and including at infinity. It diverges at infinity. So what people did was said, okay, let's replace this by some cutoff, some large number cutoff. This lambda is some large maximal momenta. You can think of a large maximum energy scale in the problem. Calculate things in and do some voodoo subtraction of infinities to get an answer. That's what people thought people were doing till the 1970s when this thing was finally understood. The problem is that in this framework, even the setup of the problem means you have to introduce a scale in the problem which I'll call a cutoff. And a cutoff of momentum is basically equivalent to putting in a lattice, because if you put things in a lattice, like if you think of like phonons, which are sound waves on a lattice, and you put anything on a lattice, then you know that the momenta are bounded between Brillouin zones, which is set by the inverse of the lattice spacing. So let me write this important thing down. Erase all that. So this comes, I'll just talk about field like this. So a momentum space cutoff I'll call lambda, is roughly the inverse of a lattice spacing. In fact, people do quantum field theory like that, which is really like doing statistical, because these are called lattice gauge theories. Fine. So you have introduced something like that. Except, what does this cutoff mean? The way we think about the cutoff in quantum field theory is that is to have a declaration that I don't know anything about the physics beyond that cutoff. I have a knowledge of the laws of nature up to this momentum lambda. Beyond that, I don't know anything. Okay? It's a declaration of ignorance of the fact. So it would be quite disastrous, wouldn't it, if this theory predicted, for example, if a mass of a particle is of the order of the cutoff. This theory would be inconsistent because you have already declared that you don't know anything beyond the cutoff. So you have to somehow find a way, and that in fact is the problem of quantum field theory, that it has a cutoff, it yet describes energies and masses much smaller than the cutoff. Okay, in the mass of you can, for example, if you do the quantum mechanics of the electromagnetic field, you can easily put a cutoff which is of the order of 100 GeV. The mass of the electron has nothing to do with that. It's way below that. So how is it possible that you look at a theory like this and it has a scale like this, and you are predicting physics at energy scales? First, you are interested in energy scales which are much smaller than the cutoff. So in particular, you should not be interested in any object which has a mass of the order of the cutoff. That just doesn't make any sense in the description of the theory. Now the significance of a mass in quantum mechanics, mass is like energy, and in relativity energy is the same as momentum. And just as if I take, so, and if I therefore if I take any system and evolve it in time and ask how do the correlations behave with time, you will typically find e to the IET, right? I mean, that's the laws of quantum mechanics. So if the thing is at rest, it will have the time dependence. I want to keep this. So the time dependence is like e to the IMT, and let's do something a little bit strange. Let's take t analytically continued to imaginary value tau, just to think about it. So this becomes like e to the IMT m tau, and this law looks pretty much like that. It's an exponential which sort of tells you how far in time your effects survive, if you are able to do such a thing. We will in fact use this procedure of analytically continuing time in quantum mechanics to relate to a real statistical mechanics problem. But if you are able to do that, what the problem of quantum field theory means is that you find a statistical mechanics problem in which the correlation length is not 10 times the lattice spacing or 50 times the lattice spacing, but 10 to the 500 times the lattice spacing. Because if the correlation length is very large, that means the correlation length in units of the lattice spacing, so if is much bigger than 1, that corresponds to a situation of having a field theory which has a mass which is much smaller than the cutoff, because here see m appeared on the numerator, here xi appeared in the denominator. So when does this happen? As we know, this does happen in statistical systems, and at very special points, when you tune parameters of a statistical system you sometimes get to a situation which are called critical points. And critical points are points where basically the correlation length in units of lattice spacing is just infinity. So this tells you, well, we are not really going to say infinity, some very, very, very large number. So this tells you that the problem of quantum field theory is namely to understand physical predictions of a theory whose all the numbers are much, much smaller than that limit of ignorance which you have declared, is equivalent to a problem in statistical mechanics, because in statistical mechanics you can have these critical points where the correlation length in units of the lattice spacing is very large. Okay. So this is the deep connection between the problem of quantum field theory and problem of statistical mechanics, which was realized in the 70s mostly by Ken Wilson, and it is this realization that basically changed physics forever. So the real time dependence in quantum mechanical systems like e to the IET, right? I mean, if you solve Schrodinger equation like I del psi del t equal to ht, and if you take an Eigen state of the Hamiltonian and look at the time dependence, so this will be psi of t goes as e to the IET. If you take, for example, correlation functions, if you like take a harmonic oscillator and calculate x of t, x of 0 expectation value, you will find the dependence which is also like this. Okay. So then I played a trick and said let's replace t by I tau, and that's how it looks like. So, and I came to an expression which is similar to this, because once I have replaced t by I tau, the difference between space and time basically disappears. We call it a Euclidean theory in that case, and then it becomes very similar to this, just to motivate the fact that there is such a connection. So this is what we want to understand. Okay. This also tells you why is it that in these situations, I mean, somehow the fact that you are asking questions at scales which are much, much lower than the cutoff of the theory is your rationale for using continuum fields, right? I mean, otherwise you wouldn't be able to continuum fields. From the point of view of a lattice, you would think that if I have a wave which is very slowly varying over the lattice at scales much, much bigger than the lattice spacing, you would think that you will be able to take this disturbance and in terms of a continuous function as well. The problem is that, and it is indeed true that for, I mean, if I have a sequence of spins which are very, very slowly varying over a very long distance, like 5,000 times the lattice spacing, it's a very good description to write that spin as a continuous spin variable. The problem is in most cases it's not very interesting, and the reason why it's not very interesting is that when the correlation length itself is like 5 times the lattice spacing, a disturbance which goes over 1,000 times the lattice spacing doesn't do any good for you, because basically blobs of more than 5 times lattice spacing decouple from each other. It only becomes interesting near critical points where the correlation length is infinite, and therefore such long distance fluctuations can be meaningfully described by these things which I'll call quantum fields. So that's the physical picture. So before I proceed on some little more details, maybe there are some questions and doubts. Any question? As already said, statistical mechanics and field theory. I will discuss the framework, the concepts behind renormalization group. I'll present specific calculations which tell you how to do these calculations. In the renormalization group, they go by the name. I'll do epsilon expansion and large n expansions. this is the subject which actually tells you what is it, what are the properties of the theory which allow you to talk about physics at low energies independent of the physics of high energies. So that's what this is about. Then I'll concentrate on a very special feature of such systems near critical points. This feature is called scale invariance, which I'll talk about in a moment. And conformal invariance. And I'll describe in not so much detail a subject which is called conformal field theory. Invented to understand string theory, has turned out to be a lot more useful to understand statistical mechanics of two-dimensional systems. Conformal field theory in 2 dimensions. And after we've understood the importance and the power of conformal symmetry, I will go over to a set of very modern methods in the topic, which something which is called a gauge gravity duality and its use to understand statistical mechanics. It's called the ADS-CFT correspondence, which brings a completely different area of physics into the discussion of statistical mechanics. The area of physics is general relativity. And I will end our discussion by describing how this particular framework, which has been developed over the past decade or so, has given rise to a geometrical meaning of the renormalization group in terms of rewriting of Einstein equations these are called Raychaudhuri equations, and how they discuss how this entire process of scale tumbling down from higher scale to lower scale in terms of geometry. Okay. So let's talk about, to begin with, some special properties of the critical points. So at critical points, throughout these lectures, I will use example of what is called a scalar field. So let me tell you a little bit what in the context of specific statistical models, what this scalar field could be. The way to think about a scalar field, if you really have a thing with a lattice, with spins or whatever have you, is to take a large number of lattice points, form a little block and write the average spin over it. And even though each of these spins will be discrete, if there are lots and lots of them, that average spin would have a large range of values, which I'll call phi of x. X you can think as the center of that blob. So in general, x can be points on a lattice. So at the critical point, so I said that away from the critical point, system has a correlation length. That means beyond a certain distance, things are not correlated, which is expressed by the fact that if you have, so away, let's say away from critical point, if you calculate the correlators of 2 of these objects, you can think of it as a block magnetization, if you wish. It has a typical behavior which goes as this by raised to the some power. For reasons which will become clear, I'll write this power as some d minus 2 plus eta, and psi is a correlation length. However, at the critical point, psi is infinite, so it goes as some constant like this. I will call this answer a scale invariant answer. And so I want to make it little precise. What do I mean by the scale transformations? Here all quantities x is distance in units of lattice space. So everything is dimensionless in this discussion. If I have a system at a lattice, on a lattice, and if I ask a question like lots and lots of points, and if I ask a question that how is this spin here correlated with this spin there, okay, you could take the original Hamiltonian and start doing the calculations and obtain an answer. In the 60s, Kadanoff had a very bright idea in which he said that, well, if I am doing this, why not do a simpler problem? I mean, he said, let's think of it actually doing it on a computer. You know, there are like many lattice points. You have to do lots and lots of, you know, calculations, lots and lots of operations on a computer you have to do to calculate this. So for example, you are calculating something like phi at 1, at phi of 2. This by definition is sum over all states phi of 1, phi of 2, e to the minus beta energy divided by the partition function. This is how you would calculate. So what Kadanoff suggested is, instead of taking this, why don't I take, for example, little blocks which are like that. And for example, take these 4 spins which are here, replace it by an average spin at the center of these blocks. In such a way that the partition function is exactly the same. Okay? So the way you technically do this is as follows. So instead of doing the correlation function, let's do the partition function is a sum over all possible values of the fields at x e to the minus beta times the energy. I want to write a new object where they are on some new lattice, new fields on new lattice, some Hamiltonian H and beta prime H prime, and I want to find the new H prime. Let me absorb the beta in the H. I can always do that. It's just one of the parameters in the theory. So I want to find the new H and H prime given a definition of phi prime such that its equality holds. I haven't done anything. I just made a change of variables in my sum. That's always allowed. Okay. But the number of these variables are much smaller than the number of variables I started in the problem. Right? They're smaller by a factor of 4. If I keep doing it, I'll keep reducing the number of these variables. So if I have a procedure to calculate H prime beginning from H, at the end of the day, in terms of a computation, I might be left with a simpler problem, with a calculating with a much smaller number of variables with a new Hamiltonian H. This of course will not be very useful if the new Hamiltonian H prime is far more complicated than what you started out with H, and that's what typically happens, except near the critical point, as we will show. As you approach the critical point, the form of this thing is very similar to that. This thing is called a block spin transformation. And what this means is, space to write. Let me think. I'll write down here. So what this means is that you made a transformation where the lattice spacing has doubled in this case, where this B is 2, B is 2 times lattice spacing. Okay? Since the lattice spacing has doubled, so I can keep doing it, many times. So let me replace it by generalize to a lattice spacing by increase by an amount of B. But because the lattice spacing has increased, this quantity x must have decreased, because this quantity is the physical distance divided by the lattice spacing, right? So what this means is that x has so that means that the new x has gone to x upon b, right? Because it's now less in units of the new lattice spacing. So if you write the physical distance is x times a, so it's x by b times b times a. So that's what it means, that x has gone to x upon b. So then if you look at this expression, so what you find is that in the blocked system, the correlation at the critical point becomes in terms of this is I'll call y, as becomes b to the 2 minus d minus eta c by y to the power d minus 2 plus eta. I've just copied this thing here just by using that definition, nothing non-trivial. So this is the first transformation. And the second thing, if you redefine fields, that means you define new fields, which I'll call phi tilde, which is now a function of y, as defined by b raised to the power d minus 2 plus eta by 2. No, that's the other way around. No, it's okay, phi of x. Then you find this is exactly the same of what we began with x replaced by y. It's obvious if we try to do it to this expression, it wouldn't work. And it wouldn't work because of this factor. It would have changed this object xi to something else. Right? So what we have just made a little more accurate is the fact that at the critical point there is a new symmetry which has emerged in the problem. And that symmetry is called scale invariance. So let me write this down. So change lattice spacing and then redefine fields. This procedure I'll call a renormalization group transformation. And at critical point, there's something called a scale invariance. So the special points in the statistical system which corresponds to quantum field theories have a special symmetry, which is scale invariance. Now, very often in physics, when you are you have a system which has some symmetry which is sort of slightly broken, it's a good idea to take that symmetry with the broken symmetry, but apply that symmetry, apply that transformation anyway, and see what happens to the system. It's a very common strategy in doing physics. So what we are going to do is precisely that. So namely, we are going to use the same transformations to a system which is a little bit away from the critical point and see what happens to that system. Okay. So before doing that, I have to remind you the mathematics of how one deals with this thing, which is the mathematics of functional integrals. Is everybody familiar with functional integrals? Feynman path integrals, you're all. Should I skip this? Yes or no? I should not skip this. Okay, good. Okay. But I'll try to give the essential steps, but go a little fast till I get to the interesting part. Write as, I'll still write with an H, where I'll write with an E, which is like this. Integral over d dimensions something like this. And then you find the partition function as the functional integral, this like this. What this means is actually quite trivial. It means that each point, I'm just talking of equilibrium statistical mechanics, so there is no time. So each point in space, you have a real number, which I call phi. So that's I write a phi bracket x. This means that you take all the points of x and all those variables, these are my random variables in the problem, and write as b e, which is of course a functional of phi of x. If the points x are discrete, it's a completely well defined mathematical integral. There is no doubt about it. The whole problem comes when you try to take huge number of points and which are all very close to each other. I'll now show that this thing, which is a completely classical problem, can be written as a quantum mechanical problem. And the way to do this is as follows. So let me take d equal to 1. So things are very simple. D equal to 1 and the space is a lattice. So the space looks like this. And I'll call the lattice spacing epsilon for some reason. I'll denote one of the sites on this lattice as I. Okay. In this case, the fields are just labeled by phi at I. I is an integer which tells you which point of the lattice you are. Extension of this to arbitrary d is basically the same, that except of one integer you have d integers which denote the the d coordinates of a point on that lattice. Once I do this exercise, the extension to higher dimensions is actually quite straightforward, so I'll not do it. So then this energy integral can be written as, so that integral I'll call this direction for a good reason, I'll call this direction tau. Okay, so one of the x's, the only x I have, I call it tau. So this is integral d tau. So let's talk of the kinetic energy. I'll call T. That's a kinetic, that's the first term in here. I'm calling it a kinetic energy with a kind of a bias. At some point I'll make this into a time. So that's why I'm calling it a kinetic energy. But you can think of it as a gradient energy if you like. So its lattice version is a sum over all sides to n minus 1. So there are 1, 2, 3 up to n minus 1 sides. This is the discretized form of the derivative. I'll multiply it by epsilon because of this d tau is there, right? So what we're going to transfer an integral into a sum, you have to take that measure, which is this. Okay? So let us write this factor e to the minus beta, I'll keep the beta, integral d tau phi whole square. Let's say I'll just rewrite this in this language. So this is e to the minus beta upon 2 epsilon phi at I plus 1 minus phi I whole square, phi of I whole square. And by a trivial integral, it is written as up to a constant. The way one verifies this is just to do this integral. This is a Gaussian integral which you can do. Once you do this integral, you will find that it gets its answer up to some constant, which is irrelevant. Is this step clear? This step? This one? This one. So this I just copied from here actually. So integral d tau, this square is given by that. I've just no, I just take one of the sums, one of the terms in I, right? There is a summation upon I. I just take, this is a mathematical identity I've written down. Nothing fancy than that. Okay? Everybody knows how to do a Gaussian integral, right? Good. No name so far. So therefore, if I take the original partition function, I for the total energy, so this will become take a product outside. So the product in the exponential just becomes a sum. Plus something I'll call epsilon f of phi. So where f of phi is this r0 phi square plus u phi 4 plus so on. And I've dumped it into f of phi because it doesn't have phi at two different lattice points. It's at local at every phi. So it can be anything you like. So this, using that identity for each of these integrals, I write down as d phi I, d p I, okay, so all I have done is just rewrite what I started out with, something pretty trivial. So now I'll start playing some games with this. a quantum mechanical Hilbert space. Forget about this expression for the moment. In normal quantum mechanics, you can have variables which are p and x with the fundamental commutation relation x comma p. Fine. X and p are operators. You can think of them made as infinite dimensional matrices which have this property. And then we also define eigen states of x here x is this x hat is an operator, this x is a real number, okay, and this is the ket vector which is this is the definition of that eigenstate of x, and similarly there is an eigenstate of p. And if you remember your basic quantum mechanics, you know that the inner product of these two things is IPX. This is all familiar? This is the momentum space wave function. The plane wave eigenstates of the momentum operator. So this is so all I'm going to do now is to replace x by phi I. I just recall, just rename by object phi I, define phi I equal to I, and then I can write e to the I p I is this formula all makes sense? Good? Okay? So therefore e to the minus I p I is given by phi I p I. So you write this I'm sometimes being sloppy when I phi I is the same as phi of I and so on. Should we drop it phi I p I and the rest of it I write is that way. And then also write e to the epsilon f phi I. To remind you, so what this means is that, but however, I know that phi I pi is just pi pi. That was the definition of these eigenstates of phi. So you can rewrite this expression as okay, but now this is the same thing as I can also put e to the phi I somewhere here, because these are, let me put this here, because those are just beta f phi I. Actually, you should put an average value of phi I and phi I plus 1. I'm sort of ignoring that little subtlety out here. But now we can see that so far as the integral of our pi goes, there is no pi anywhere here, but there is a ket and a bra. But by the completeness relationship, this just becomes just integral of phi I what happened? There was a 2 beta here. Okay, minus epsilon okay. This is for each of the factors, and if I take, so if I do this integral, so this is like d phi 1, d phi 2, so on, and then phi I, I'll call this a new thing, h, so phi 1, phi 2, phi 2, phi 3, and so on, one after the other. That's what the product means. So if I now make this thing into the one-dimensional line into a circle, so that phi n is the same as phi 1, so that's periodic boundary conditions on the circle, then this thing can be written as a trace what happened to the epsilon? Yes, it is there. So I didn't write what h hat is. So h hat is where was that? Pi I square by 2 beta plus beta f. So it's there. Actually, epsilon multiplies the whole thing. Did I answer your question? There was an epsilon times f here, right? Oh, sorry. This is beta epsilon, right? That's it. Okay? So if I think of that one-dimensional line as a circle, so that I put periodic boundary conditions and put phi n equal to phi on, this thing can be written as a trace of minus th, where t is n times epsilon. Is this clear? Phi, they don't commute, that's right. But that's okay, this is on epsilon, right? It's a small number here. Right. Yeah, because I can stick it up into little, it's a lattice. Okay. So I should say that epsilon is very small. I've been very careful about that. Epsilon is a very small number. So what I have done, I started with a classical statistical mechanics problem. There was no operators, quantum mechanics anywhere here, and I ended up a statistical mechanical problem in one dimension, equilibrium statistical mechanics in one dimension. And when I take the limit, epsilon goes to 0, n goes to infinity, and a t finite, it represents the trace of an operator which I have written as e to the minus t times h. This capital T is like the total size of the system, which is the lattice spacing times the number of sides of the lattice. And this operator is something which is very familiar to us. And the reason why this operator is very familiar to us is is as follows. Let me test this. Is e to the minus IHT, where t is the time. So if I take t to be minus I times tau, this is called a process which is called Euclidean time. This operator becomes e to the th, e to the tau h. So a one-dimensional classical statistical mechanical problem can be written as a zero-dimensional quantum problem. It's a zero-dimensional quantum problem because if you look at the Hamiltonian pretty much looks like a typical Hamiltonian in quantum mechanics textbooks. If you do exactly the same exercise for a statistical problem which is defined on a d-dimensional lattice, so what you will find is that the d-dimensional statistical problem is equivalent to a d minus 1 dimensional quantum mechanical problem, quantum field theory problem. And the reason I called it quantum field theory rather than quantum mechanical is because the variables pi and phi, which were there in the theory, it's a pi square, are replaced by phi is phi of I, right? They're replaced by an operator phi, which is function of x and t, and the operator, the Heisenberg operator pi I, is replaced by a canonical conjugated operator. These have the commutation relations. The delta function. It's completely analogous to quantum mechanics. There is nothing different from quantum mechanics. So a field theory which has some number of lives in some number of space dimensions, we have established a very precise way in which what is equivalent to a statistical problem in one higher dimension. This is the correspondence which we are going to use. Okay. Huh? No, so we proved this for d equal to 1. We showed that a one-dimensional statistical mechanical problem is just quantum mechanics, namely a Hamiltonian p squared plus v of x kind of thing, right? So what I'm saying, this is the stuff which I haven't shown, is that instead of starting out with points on a line, if you actually started out with the points on a, say, a two-dimensional lattice, then instead of the variables phi I, so phi I was a shorthand notation for phi, and this I was some time variable. Now we'll have another variable, so let me call it x. This is the second dimension of the statistical mechanics problem. And if you repeat the same exercise, what you will find that you will get exactly a problem with a Hamiltonian whose canonical variables are things like our problem are canonical variables x, phi and pi, which were like x and p in quantum mechanics. So now we have a phi which is a function of x. The x is the other directions. Okay, and you'll get similarly a Hamiltonian, which is a standard, one of the theory Hamiltonian. So these are d dimensions. Everything is Euclidean, so there is no real time. And then e to the minus some action, and the action is d dx times something. I'll not write down, but I'll write down the action later on. Now, how do you define this integral? A good way of defining this integral is actually to do a Fourier transform. So this is the precise definition of the integral. So you put x in a box. X is a point in a d-dimensional box. So then I write a Fourier decomposition of volume V. The Fourier decomposition of this thing is, I hope I put my d-dimensional periodic box of volume V. These k's are momenta which are in a Brillouin zone, and epsilon is a lattice spacing. Okay. So all I have done, I have taken a real space field and written in terms what I will call momentum space fields just by a Fourier transform, and I can always do it for a function. I mean, I can always do it if you have a lattice and have a set of real numbers at each point of the lattice. I can always do such a thing. The transformation these variables, the usefulness of doing this is that I get gotten from one discrete set of variables to another discrete set of variables by actually a unitary transformation. So what I mean by this thing precisely is as follows. So I should tell you what the dimensions are. So k I'll write as components k0, k1 to k d minus 1 is defined as follows. Okay. Now there is a reason for doing this, and the reason for doing this is as follows. This was a real field to begin with. These are of course complex. The Fourier transforms of real field are generally complex, but because this is real, there is a non-trivial relationship between phi star of k has to be equal to phi of minus k. So all the phi of k's are not independent variables. There are too many of them, and restricting all the modes to have one of these momenta to be positive is one useful way of picking out an independent set of variables. Otherwise you will be double counting a lot. So once you do that, the integral is mathematically well defined, and I'll just write down for you the rules of doing these integrals. So symbolically, when I write d phi of k, this is what I mean by that. So let me write d phi of k. So d phi of x, I'll write as the d phi of k is this object. And then if I write some function of k, phi of k mod square, the result of this thing is a product over all k This is just a Gaussian integral because the way I have separated out, and if you just, I'm not going through all the steps that lead to this, but you can trust me that this is just a simple Gaussian integral of independent variables, and the usefulness of going to this thing is that I've written everything that this is just an application of the fact that if that's all I've done. Okay, so given that, let's now do a little exercise. Yeah. I threw away the zero mode. I'll ignore it for the moment. In cases when you discuss things like spontaneous symmetry breaking, those are important. And if I ever come to that, I'll discuss this. But let me ignore that for the moment. Yeah. But let me just do this and end today's lecture. It will take another, it can take another 10 minutes maybe. I think that should be good enough. I'll now take an expression like this and perform an RG transformation. So let me just precisely tell you what. I haven't specified it. Any function of k you like. Actually take it a function of k square rather than a function of k. Spacing, which I call epsilon or a or whatever you like, I'll now go over to dimensionless momenta. And similarly dimensionless fields, but the dimensionless momenta I'll call q, which is k times the lattice spacing. In our units, the momenta has dimensions of 1 upon length. So if I multiply it by length, the answer is dimensionless. Okay. The fact that k goes from, so k is pi upon e, and in what I'm doing now, let's set pi equal to 1, doesn't matter. So what this means, modulus of q is basically less than 1, pi equal to 1. Okay. I mean, those factors are not important in what I'm going to do. This immediately tells you the relationship between what I call a position space cutoff, like a physical lattice spacing, and a momentum space cutoff, which is the maximum value of q that is allowed. Okay. So this is the cutoff when I was talking about is that bound of ignorance of our theory. And I am now going to do the functional integral product over all q d phi of q, and everything is dimensionless, and the only thing is what I meant by 0 and 1 is the magnitude of q lies between 0 and 1. So this is my cutoff quantum field theory. Okay, it has a momentum space cutoff lambda. I've used that lambda is like 1 upon epsilon. I've used that cutoff to define some dimensionless momenta, which now goes from 0 to 1. Everything is dimensionless, everything is a number, you can put it on a computer, write a program and calculate this, no problem. Let me take a q square function C0 plus C1 q square plus C2 q fourth plus C1. I want to now write down this q, so this phi of q as, so this is like q goes from 0 to 1. I'll write this from q going to 1 to b, d phi of q, b to, sorry, 0 to b, d phi of q. So what I have done, we have taken my variables of integration and separated out into two parts. One part has this momenta whose magnitude lies between 0 and b, sorry, 0 and 1 upon b. I'll use the other thing. B is a number which is bigger than 1, so 1 upon b is smaller than 1, and the rest of it is between 1 upon b and 1. Now, remember an RG transformation take a lattice spacing and increases it by a factor of b, right. So that means it takes the momentum space cutoffs and decreases by a factor of b. So if I were able to do this part of the integral, then I should be able to write down the partition function entirely in terms of variables which lie between q equal to 0 and 1 upon b. That means the momenta lying between 0 and lambda upon b. But this is exactly what I wanted. I wanted to see what happens to the theory if I were to write it in terms of variables which are appropriate to a lower value of the cutoff. So let us try to do this integral. The beauty of this example is that you can do this integral. And the reason why you can do this integral is that if you look at what is happening here, there is a phi of q and a phi of minus q. It is the same q everywhere in here, right. So that integral can in fact be written as 0 to 1 upon b plus exactly the same thing 1 upon b to 1 okay. So I have to do this integral. So let me use this later on. This integral completely separates. There is an integral from q to 1 upon b to 1 d phi I'll write this as dq vector because it's too much to. Integral. Okay. So I have managed to write down the theory entirely in terms of degrees of freedom whose momenta don't go all the way to the cutoff of the theory, but somewhere below that cutoff of the theory. Okay. This is an example of what is called an effective field theory. I can use this theory, this functional integral, to calculate all quantities which relate to dimensionless momenta which are less than 1 upon b. It is senseless to use this, to use it for dimensional momenta bigger than 1 upon b, because it just simply doesn't appear in here. Okay? The difference between this and what I started out with, which had an integral from 0 to 1, is that all these integral limits are 0 to 1 upon b rather than 0 to 1. What I want to do now is to do two things. Remember, the physical momenta, q physical, was q divided by the lattice spacing. So a p physical is given by b times q times the new lattice spacing. So let me write. No. Okay. So what has happened is that if I change the lattice space, because lambda upon b is the new cutoff of the theory, but the coefficients of that function, and I'll call these coefficients as coupling constants of the theory, have now changed as a result of that. The new effective theory, which describes my physics at low momenta, is very much like the theory I started out with, but with different values of the coefficients. And the coefficients have a very interesting form. And this is my last comment. I did it by a factor of b. A factor of b was always bigger than 1. Okay? It increased the lattice spacing. So suppose say b was 2. Okay? If I keep doing it over and over again, I will keep getting these recursion relations over and over again. C0 double prime will be b to the 4 times C0. Right? So as a result, I draw a picture which is like this. So one thing you note is that by my choice, and that choice is intimately connected to this definition of the field. This is something which is called field renormalization. Okay? By that choice, I have ensured that the term which is q square phi square, which is like grad phi whole square, that basic term, that coefficient did not change. I insisted that that coefficient remains exactly the same. But given that thing, I could predict how the other coefficients change. Okay? And as I see, there is only one coefficient in the theory, C0, which keeps increasing as I keep increasing the lattice spacing. Okay? All the other coefficients decrease as that happens. In fact, I can draw a picture where I plot the values of C0 and the value of C2. If I start at this value of C2 and that value of C0, if I do one step of this process, this will correspond to a smaller value of C2 and a bigger value of C0, a point like this. Do one more step, it's a point like that. So if I keep doing it, these points all represent the theory of same physics. The theory of same physics means that given a scale, it tells you everything about momenta less than that scale. You had a question? This tells you is that if I am interested in questions where the momenta never exceeds, it doesn't go all the way to the cutoff but lower than the cutoff, I can do that by this procedure, which is a renormalization group transformation, which involves rescaling the momenta and rescaling the fields, and can derive everything in terms of an effective theory. And in that effective theory, once I have done this many times, the answer stops depending on most of these coefficients. It starts depending only on one single coefficient in the theory, which is C0. You can explicitly check this by calculating, maybe I leave this as an exercise, by calculating the 2-point correlation function. The 2-point correlation function of q minus q, that will be given by actually by C0. Let's just put two of them. Q4, and you can check by taking the Fourier transform of this that if as you go to very long distances in position space, then what you will find, all these higher things essentially do not enter into my answer. Okay? You might think this is magic. How did it happen? How did it happen? I started out a theory with 200 parameters, and I have managed to reduce that theory to a theory of basically one parameter. The answer is, it happened only because you are asking very specific questions. And this is the secret of quantum field theory. Quantum field theory takes a theory and asks a limited set of questions. It asks a set of questions which relate to physical processes with energies and momenta which are much, much smaller than the cutoff. And what this tells you in a very simple example is that for such processes, most of the parameters of the microscopic theory are what I call irrelevant. The technical terminology for this is that C2, C4 are irrelevant. C0 are relevant. And C1 is called marginal, because it neither decreases nor increases under the RG transformation. Quantum field theory works only because typically we have a finite number of relevant couplings in the theory. Most quantum field theories you write down have a finite number of relevant couplings. It doesn't really matter whether there are 500 irrelevant couplings at the Planck scale. This is why I can keep doing physics at our ordinary energy scales without any detailed input from microscopic physics. At the same time, it is important to realize that the coefficients of the low energy theory, which are this C0 prime, C1 prime, and C2 prime, are actually determined by the coefficients of the high energy theory. Okay? So those values of the relevant couplings are determined in terms of what you started out with. It's just that the values of the irrelevant couplings are really irrelevant. It doesn't occur in the low energy physics. Okay? Now this is a very trivial example because it's easy to work out. But I think it actually drives forth the main philosophy of the subject. In the following lectures, we'll do a lot more non-trivial examples of this, which include interacting quantum field theories, and which include behavior under the renormalization group, which are a lot more non-trivial and interesting. But I think the basic lesson remains the same. Okay. In the old days, this property of quantum field theory, namely that it would only depend, the low energy physics only depends on a few parameters, used to be called renormalizability of a quantum field theory. And at that time, people used to think that there were theories which were not renormalizable, and they were very bad because there was nothing to it. In the modern way of thinking about it, there's absolutely nothing wrong with non-renormalizable theory. We will in fact show that they make perfect sense, except that what they tell you about the low energy theory is very limited. It tells you something very trivial. The low energy limit of non-renormalizable theories are in fact trivial theories. In the statistical example I talked about, low energies means energies much, much smaller than the cutoff. In conventional quantum field theory, I mean pre-Wilson, people used to think of no cutoffs. It was continuous space-time, cutoffs were infinity. So low energy in that theory, where the cutoff is taken to infinity, means any finite momentum. Okay? But nowadays we don't think about physics that way, because we do not really, cannot say with confidence what is the physics at Planck scale, and it will be a disaster if we needed to know the physics at the Planck scale to make predictions about quantum electrodynamics. And that's why the fact that you have a finite number of relevant couplings plays such an important role in quantum field theories. Okay? So the rest of it will be a little more non-trivial calculations.